Hello, this is Physics 104A, the homework solutions for Chapter 11. Starting with number 11, a car is headed north at 70 kilometers per hour. Give the magnitude and direction of the angular velocity of its 62 centimeter diameter wheels. All right, let's draw this with compass direction, so north going up, north, south, east, west. And so we're looking bird's eye view at the car, and it is traveling north. And we want this in MKS units, so 70 kilometers per hour. You should be able to convert that to 19.4 meters per second. And we have the wheels have a radius of 31 centimeters or 0.31 meters. And let's first think about the direction. We come over here to the map, and we see it's going to the right, and you can imagine the wheels are rolling. So you can take your right hand and with the palm down and have your fingers roll like the wheels roll, and your thumb of your right hand should be pointing to the left. And so that is the direction of omega, the rotational velocity. And so we want to know the magnitude of that velocity, angular velocity. Since v is omega times r, we have omega is v divided by r. And so we take v, 19.4 meters per second, divided by the radius, and that is the angular velocity of the wheels. So 63 radians per second, and that vector points to the west. Number 15. A 12 Newton force is applied at the point x equals 3, y equals 1 meters. Find the torque about the origin if the force points first in the x direction, second in the y direction, and third in the z direction. All right, I've drawn a picture for these, and let's write out the given information. So force is 12 newtons. There is the lever arm, 3 meters, 1 meter. And for part A, it says it points in the x direction. And so as a vector, that force is 12, 0, 0. And here I've drawn it. Now drawing it gives you a sense of the direction that it's going to be. So imagine that the blue, the vector, imagine that's a wrench that's being pushed by the force. And you can see it's going to be pushed in the clockwise direction, which is the negative direction. And if you use your right hand, to curl, what direction is that blue, the r vector, going to be pivoted, going to be rotated? Your thumb should point into the page. So that's the negative z direction. Now, I've used this method that I've taught in class, that if we're doing the cross product of two vectors, we're going to take the first vector, so r cross f, and we have 3, 1, 0, and then repeat it, 3, 1, 0. And then the second vector, force, 12, 0, 0, 12, 0, 0. We're going to cut out the first column and the last column, completely ignore them, and then we do the crisscross. So 1 times 0 minus 0 times 0. That's the x direction, the I hat component, and that's 0. Next, 0 times 12 minus 3 times 0. That's the y component, the j hat, and that's 0. And then we have 3 times 0 minus 1 times 12. That's negative 12 in the z direction. So it's going to be negative 12 k hat Newton meters. And that corresponds with, using the right-hand rule on the picture, we could see it should have been in the negative k hat direction. Part B, now the force is completely in the y direction. So you can see this picture that I've drawn. If you imagine again that the blue, the r vector, is a wrench that's being pushed on, it's being turned in the counterclockwise direction. That's the positive direction. If you're doing it with your right hand should come out of the page in the positive z direction. I'll use the same method. So 3, 1, 0, 3, 1, 0 for the r hat. For the f, it's 0, 12, 0, 0, 12, 0. Ignore the first column and the last column. And then we do 1 times 0 minus 0 times 12, that's 0. 0 times 0 minus 3 times 0, that's 0. And the only part that's there for torque is the z component. 3 times 12 minus 1 times 0. So that's positive 36 in the z direction, 36 k hat Newton meters. And then finally, the part C has the force going in the z direction. I didn't draw it, but the force is 0, 0, 12. And so we're going to do the same method that I've used, but now the force we're going to write out on the lower row, 0, 0, 12, 0, 0, 12. And then we do our crisscrossing, 1 times 12 minus 0 times 0, and that gives 12 I hat. Plus 0 times 0 minus 3 times 12, so that's minus 36 j hat. And then 3 times 0 minus 1 times 0, and that's 0 in the k hat direction. So we end up with a torque of 12 I hat minus 36 j hat Newton meters. Number 18, express the units of angular momentum 3 different ways. Using only the fundamental units kilogram, meters, and seconds, then in a form involving newtons, and then in a form involving joules. So this is just a good exercise, little puzzle in manipulating, thinking about units. And the way we do dimensional analysis, if you want to know what unit something is, find some formula that uses it. So angular momentum, you can think of it's r cross linear momentum, or r times m times v, which comes from that. And think of the dimensions there. R is meters, mass is kilograms, v is meters per second, so throw them all together, and we get kilograms meters squared per second. If we want to get it in, it just vaguely says some form involving newtons. And with some imagination, we can come up with a variety of these. But here's one. We know that it's kilograms meters squared per second. We know that a newton is kilograms meters per second squared. So if we separate out from this kilograms meters per second squared, which is newtons, multiplied by meters and seconds, we can see that that's going to be equal to that. So it's newtons, meters, seconds. And then once we get that, newtons, meters, seconds, do it in some form that involves joules. Well, a newton meter can be thought of as a joule, so it could be joules seconds. Number 19. Use data from Appendix E to make an order of magnitude estimate for the angular momentum of our solar system about the galactic center. And so something that is useful to know when we think about our solar system, we can think there's lots of planets, there's many, many moons, a few hundred moons, but most of the mass, something like 99.9% of the mass of our solar system is the sun. So we can actually ignore all the planets. It's the sun that's the major mass. And if you look at Appendix E, it tells you the mass of the sun is 1.99 times 10 to the 30th kilograms. And I've just here said roughly 2. We're just making an estimate here, 2 times 10 to the 30th kilograms. Because the problem, number 19, says make an order of magnitude estimate. So 2 times 10 to the 30th kilograms is close enough. And if you look at the masses of all the other planets, even like Jupiter, is 1.9 times 10 to the 27th kilograms, and Jupiter being the most massive. So this is going to be a close enough estimate right here. Now, we're going to need, here I've drawn a picture of our solar system, which effectively has that mass of 2 times 10 to the 30th kilograms. It's going around the galaxy's center. So we need to know the distance from our solar system to the center of the galaxy. And in Appendix E, one of the columns says mean distance from the central body. And there's a little notation at the bottom. It says central body is the galactic center for the sun. Okay, so that's exactly what we're looking for. And it says that that's 2.6 times 10 to the 11th, but then you look at the column, what are the units on the column? 10 to the 6 kilometers. So it's 2 times 6 times 10 to the 11th times 10 to the 6 kilometers. Well, with all these powers of 10, you're going to turn kilometers into 10 to the third power. Say you have powers 11, 6, and 3. That's going to be a total of 2.6 times 10 to the 20th meters. So we know M, we know R, and for V, we look in the very last column and it says the mean orbital speed. Again, we're just looking at for the sun in kilometers per second, 250 kilometers per second. Let's call that 250 times 10 to the third meters per second. And those are the things we need. That angular momentum is mass times the radius of the circular orbit times v. Put them all together and we get about 10 to the 56 power. And in the last problem, problem number 18, we used we found different units, ways of expressing this. I'm going to put it in joules seconds. So 10 to the 56 joules seconds. Number 22, a 7.4 centimeter diameter ball has mass 145 grams and is spinning at 2000 RPM. Treating the baseball as a uniform solid sphere, what is its angular momentum? So we've got the radius. Take the diameter, divide by 2, so it's 3.7 times 10 to the negative 2 meters. We've got the mass. Here I've converted 2000 RPM to radians per second, so 209.44 radians per second. And rotational inertia for a solid sphere is 2/5 mr squared. So the angular momentum is the rotational inertia times omega. And I've calculated rotational inertia. I didn't write down the numbers. I didn't write down the full calculation, but it's 2/5 times, here's the m, here's the r squared. You should get 7.94 times 10 to the negative 5th times omega, and we get 1.7 times 10 to the negative 2 joules seconds. Number 23. A potter's wheel with rotational inertia 6.4 kilograms meters squared is spinning freely at 19 RPM. The potter drops a 2.7 kilogram lump of clay onto the wheel where it sticks 46 centimeters from the rotation axis. What is the wheel's subsequent angular speed? All right, so let's look at the picture here. We've got this wheel that's spinning, and there's a clump of clay that fell, not on the edge, but 46 centimeters from the rotation axis. And we don't immediately know what the radius of the wheel is, except it's obviously no less than 46 centimeters. All right, so I've written out the given information. Mass 2 is 2.7 kilograms. R2, so we're talking about the clump of clay. We know that the wheel itself, I1, is 6.4 kilograms meters squared. We know the original, so we'll say omega 1, 19 RPM. And let's first find the moment of inertia for the lump of clay. I2 is m2r2 squared. It's just 1 point mass. And you can calculate that and get 0.57132 kilograms meters squared. Now we're going to use conservation of angular momentum. And so the initial condition is just the wheel spinning. So the moment of inertia, the angular momentum of just the wheel. So I call that L1. And that is I1 times omega 1. After the interaction, we have what I'll call L1 plus 2. So the rotational angular momentum of the wheel plus the clump. And that is I1 plus I2, so it's their collective rotational inertias times omega. And now we're just going to solve this for omega. So omega is I1 over I1 plus I2 times omega 1. We have I1 in the numerator. I1 plus I2, well, we solve for I2, add I1 to it, so 6.97. And so that forms a ratio there, times 19 RPM. And when you solve that, you get that it's moving at 91.8% how fast it was moving. So 0.918 times 19 RPM, and it's 17.4 RPM. Number 25. A uniform spherical cloud of interstellar gas has mass 2 times 10 to the 30th kilograms. has radius 1 times 10 to the 13th meters, and is rotating with period 1.4 million years. The cloud collapses to form a star 7 times 10 to the 8th meters in radius. Find the star's rotation period. All right, good conservation of angular momentum problem. We have the mass, which by the way is the mass of the sun. It says to consider it to be a uniform sphere, so 2/5 mr squared is appropriate. There's R1. And period 1 is 1.4 times 10 to the 6 years. Then it says the radius after it has collapsed is R2, 7 times 10 to the 8th meters. Let's use conservation of momentum. L1 equals L2. So L1 is I1 omega 1 equals I2 omega 2. And for omega, we can think that that is, well, we're given the period. And remember that omega, the angular frequency, is 2 pi over the period. It's 2 pi times the frequency in hertz, which is 2 pi over the period. So let's call that 2 pi over T1. And on the right, 2 pi over T2. Now be careful. You see that I've divided both sides of the equation by 2 pi. Don't just leave the parentheses as T1 and T2, because those are in the denominator. Those are 1 over T1 and 1 over T2. So you could rewrite the left-hand side, I didn't do it, but as I1 over T1 equals I2 over T2. When you solve for T2, you should get that it's I2 over I1 times T1. And now let's figure out those rotational inertias. So I2 is 2/5 mr2 squared. I1 is 2/5 mr1 squared. And the mass stays the same. So 2/5, those will divide out, the m's will divide out, and we're left with the ratio of R2 over R1 squared times T1. And then we can plug in those radii, 7 times 10 to the 8th in the numerator, 1 times 10 to the 13th in the denominator, and then we're going to square it and multiply by 1.4 million years. And when you take that very small fraction and then square it for an even smaller fraction, that 1.4 million years gets reduced to 0.00686 years, which is about 2.5 days. Number 32. This comes off of example 11.2. Astronomers observe a neutron star of radius 7.1 kilometers and determine it's rotating at 21.9 RPM. If the stellar core that collapsed to form the neutron star was originally rotating with a period of 49.3 days, what was its radius? All right, so this is very similar to the previous problem. Let's see what we need to do to solve it. We have R2, so the final radius is 7.1 kilometers. And we have the original period, so I'll call that T1, 49.3 days. Now I turn that into minutes. You used to me turning it into seconds for MKS units, but the frequency 2 is given in RPM, revolutions per minute. So I'm just keeping with consistent units here, getting that in minutes, so that when we take frequency 1, the original frequency, it's 1 over the period. So that's going to be revolutions per minute. So now we have frequency 1, revolutions per minute. Frequency 2 is revolutions per minute. And here I wrote out, I started to write out omega 2 is 21.9 RPM, and then I realized, well, actually that's more in keeping with saying frequency 2. There's just this relationship, they're off by 2 pi from each other, omega 2 pi times frequency. Let's see what happens when we apply conservation of angular momentum. I1 omega 1 equals I2 omega 2. And so treating them as uniform spheres, 2/5 mr1 squared on the left, 2/5 mr2 squared on the right. Look what I did with omega. Omega 1 is 2 pi f1. Omega 2 is 2 pi f2. Now the 2 pi's are going to divide out. So actually, we could have just substituted those omegas for f's. and it wouldn't matter. But just to be safe, we do that and see that the 2 pi's divide out. When we divide everything out that will divide out, you should be getting this ratio that R1 is the square root of F2 over F1 times R2. So the final frequency, 29.9 RPM, the original frequency, 1.4086 times 10 to the negative 5 RPM. And I think back to up here when I chose to do it in minutes and RPM. And I chose that because the final frequency was given in RPM. It really doesn't matter what units you use. It could have been radians per second. It could have been revolutions per second, revolutions per minute. It's just be consistent with the units. And the reason is when we come down here, we're looking for the ratio between them. They should have the same units. So RPM and RPM divide out. And so when we calculate this, square root multiplied by 7.1 kilometers for the final radius, we get an initial radius of 8850 kilometers. Number 39. A thin rod of length A and mass m is rotating about a perpendicular axis through its center. The rotation rate is such that the ends of the rod move with speed v. Find an expression for the rod's angular momentum about its rotation axis. All right, so we think about the angular momentum through the rotation axis. And let's go down to the bottom line here. So that's going to be L equals I omega. And you know, you can look this up in the chart, and we've used it in class a few times, that a rod being rotated through its center, its moment of inertia is 1/12 m times length squared. And in this problem, the length is A. Here, I've written it up here. The length is A, so it's 1/12 m A squared. Now, we're also going to need omega. And so we are given that a point on the end of the rod is spinning with a speed v. Let's get that in terms of omega. So remember that v is omega r. The picture is helpful to see what is the r, the radius of such a point of its spin, and that's half of a, so a over 2. So v is omega a over 2. Solving that for omega, we get 2v over a. And now we have rotational inertia I, we have omega. Let's plug those in together. So angular momentum, I times omega, is 1/12 ma squared times 2v over a. Clean that up, simplify it, and you get mva divided by 6. Number 42, nice little math problem here. The dot product of 2 vectors is half the magnitude of their cross product. What is the angle between the 2 vectors? All right. So we want to know theta. Here's the given information. The dot product is 1/2 the, it says the magnitude of their cross product. So here I've written that out. And now let's think about equivalencies to these things. The dot product is a times b times cosine theta. The magnitude of a cross product is AB sine theta, and we put the 1/2 there. Set those equal to each other. The A and B divide out, and we're left with cosine theta equals 1/2 sine theta. Let's divide both sides by cosine theta, multiply both sides by 2, so that gives us 2 equals sine over cosine, which is tangent. So tan theta equals 2. And from there, take the arctan of 2 to see what the angle is, and you should get 63.4 degrees. Number 44, there's a picture in the book, and I've drawn that picture on the page here. Shows the dimensions of a 880-gram wooden baseball bat whose rotational inertia about its center of mass is 0.048 kilograms meters squared. If the bat is swung so its far end moves at 50 meters per second, find its angular momentum about the pivot P, the constant torque applied about P to achieve this angular momentum in 0.25 seconds. Hint, remember the parallel axis theorem. All right, it's also telling us, I haven't drawn this in the book, but from the center of mass to the end of the bat is 31 centimeters. All right, well, it's giving us the rotational inertia, about the center of mass. There it is, 0.048 kilograms meters squared. It's giving us V, and if we want to know what is the angular momentum, that's going to be I times omega. We need to solve for omega. So omega is V over R, and it says the point is moving 50 meters per second. And then we need to read the problem to see what point are we talking about. It says the far end moves at 50 meters per second, and it's being rotated about point P. So this is 0.43 meters. And then I haven't written it, but it says this is from here to here, the center to the end is 0.31 meters or 31 centimeters. So you add those together. So from P to the end is a total of 74 centimeters or 0.74 meters. So you should get that this point on the end is moving with an omega of 67.568 radians per second. All right, now, if we're going to find angular momentum, we found omega, now we need I. And so we think, what is I? What is the moment of inertia of this essentially, well, we don't have to say essentially a rod because it's telling us what the moment of inertia about the center of mass is. Parallel axis theorem right here. The moment of inertia when rotated about a certain axis is the moment of inertia about the center of mass plus the mass times the distance between the two axes squared. And it's giving us the moment of inertia about the center of mass. And then we're going to add the mass times the distance between the two axes, 0.43 meters, and square it. So when you do that, you should get 0.210712 kilograms meters squared. So here we've got the moment of inertia when it's rotated about point P. Up here we found omega, multiply them together, and that is the angular momentum, 14.24 joules seconds. Then it says, what is the torque applied about P to achieve this angular momentum in 0.25 seconds? And remember that torque is the change in angular momentum over time. And to achieve that angular momentum, so we say starting from rest, so the change in angular momentum is that 14.24 joules seconds, or Newton meters seconds, divided by the time of 0.25 seconds, and we get 57.6 Newton meters. And I wrote parenthetically here, remember that's not joules. So if you come over here, joules seconds divided by seconds, seconds divide away, you might be inclined to use the units of joules. But remember, torque, even though dimensionally it's the same as joules, we don't call it that, it's Newton meters. And remember, in a previous problem in this homework set, we found another way of expressing angular momentum as Newton meters seconds. So that might have been more appropriate here. Newton meters seconds divided by seconds is just Newton meters. Number 60. A time-dependent torque given by tau equals a plus b sine ct is applied to an object that's initially stationary but is free to rotate. A, b, and c are constants. Find an expression for the object's angular momentum as a function of time, assuming the torque is first applied at t equals 0. All right, so we have our time-dependent torque, a plus b sine ct. It says initial angular momentum is 0. And we want an expression for angular momentum, L. And how does that relate to torque? Well, we have torque is dL dt. Multiply both sides of this equation by dt, and we get dL equals tau times dt. And here it is. Now, we're going to take the integral of both sides. So when we take the integral of dL, that's going to be L. And then integral of tau dt. So let's do it. L is, and here's the integral, and it says we're starting at time 0 and finishing at some time t. Here's the torque equation. And now we're going to find the integral. So the integral is at, so the integral of a dt is at, plus b times sine ct, the integral of that, is b times negative cosine ct over c. Now, I want you to pause and go through that on your own. And this is a good time to remember some of our basic rules of integration. And don't just go with this, believe me, because I said it, but actually work through it, make sure you get this result. And we're going to take the integral from 0 to t. And so I'm going to clean that up with the 0 and inserting the 0 and the t. So first inserting the t, that's going to be at minus b over c times cosine ct. And now don't just disregard that 0 down below because not all the terms will zero out. Certainly the a times t will zero out because it's a times 0. But this other term, that will not go to 0. So when you plug in for time equals 0, it's, remember you're subtracting these, and then it's negative b over c times cosine of 0. And so that's going to give you plus b over c. Again, work that out on your own. Make sure you get what I get. So this is the answer right here. However, we can clean that up just a little bit, and we can factor out the b over c. So I get at plus b over c times 1 minus cosine ct. And that is the end of the Chapter 11 homework. Have a great day.